class, if you recall, we were talking about the various design for testability techniques which make life easier for the test engineers in terms of the effort they have to put in for testing. Now, in the structured DFT techniques that we have talked about, we talked about techniques like scan chain and partial chain, which are very popular methods which are followed in the industry, whereby given a design we add scan chains to it, with the net result is that the resultant circuit whatever we get is much easier to test. Okay. There is another general philosophy which is also in widespread use, that is called built-in self-test. Well, here we are trying to add some more circuitry inside the chip so that the chip can test itself, but there are a number of issues that need to be addressed here. So, in the lecture today we will try to address some of these issues which are posed by the Bist built-in self-test techniques that are used. So, first let us try to see what is this built-in self-test technique and what does these involve. Well, built-in self-test is useful for field test and diagnosis. Field test means in the exact environment where you are using the chip in terms of the application, you can test the chip there itself. In contrast, if you are using design for testability techniques, then the chips have to be tested in a special laboratory where you have an automated test equipment installed. And since these ATEs are very expensive equipments, so having Bist and using it for testing is in general much less expensive. Now, talking about field test and diagnosis, so earlier many people used some kind of software tests or diagnostics to test the modules or the subsystems which are working correctly or which have failed. But the problem with software tests is that the hardware fault coverage is not that high, and moreover, since these are software programs which are running, they are relatively slow to operate. So, a better approach is to have some special hardware mechanism. Using some special purpose hardware, we can have this built-in self-test mechanism. So, if you have this, the system test effort will be much lowered because already there is some hardware inside the chip that will take care of almost everything. Because of this, the system maintenance and repair activities will be much better, and you can have better diagnosis at the component level, because if a component fails, the component itself will announce that, well, I am bad. Okay. So, now let us see that what are the major test problems that are tackled or handled in Bist techniques, which otherwise would pose a big problem to the test engineers. Okay. So, the major test problems that are elevated by Bist are as follows. Well, you know that the number of components in a chip are increasing day by day, but the number of pins of the chip is not increasing in the same proportion. So, increasing chip logic to pin ratio is a major concern, which means that the controllability and observability of the logic inside the chip is going down every day. So, if you have some special purpose hardware inside the chip to test the logic inside, so it will be much beneficial. Well, this is a related point, increasingly dense devices and of course faster clocks. This is one important issue. Nowadays, we run the circuits at much higher clock frequencies, but in techniques like design for testability DFT scan path, there we really do not test the circuit at its full speed or full frequency, because we need to scan in the data in the scan chains and then only we can apply a test vector and we can see the output. So, the frequency at which we are actually operating the circuit is much lower than the actual intended operating frequency. But in Bist we can do the testing at the actual fast clock rate. and the increasing test generation and test application times, that can also be alleviated by Bist because it is done automatically inside. And since we are using automated test equipments and the size of the test vectors required is increasing day by day, so the memory requirement of ATEs is also increasing. So, these problems are also addressed, and ATEs which work at 1 gigahertz clocks or higher are very expensive. This is one issue, and testability insertion with respect to DFT is not always very easy, because designers normally designer work at the behavioral level. So, the CAD tools automatically will translate the behavioral level into gate level. So, when we talk about inserting some testability, you can say features at the gate level implementation design, so it becomes a problem. Okay. So, designer may not be very much familiar with the gate level logic which the synthesizer has synthesized, because after optimization typically it is very difficult to identify the gate level logic components and correlate it with the higher level behavioral level components. Okay. So, these are the problems, and now let us try to see that what are the different components of costs that are involved in having a Bist implementation. Okay. So, the first and obvious cost is clearly the chip area overhead for the additional hardware that you need. Well, if we want to do the testing inside the chip, we need two things. We need a hardware pattern generator inside the chip, and we need some sort of a hardware response compactor or response calculator inside the chip, and there has to be a special purpose controller which will be controlling these two. So, these are the three additional hardware blocks that we need inside the chip, and for these we need these extra chip area overheads. Not only that, we need additional pins. We must have at least one additional pin which will tell the chip that, well, now I want to test. To activate the Bist operation, there can be one pin. 0 means normal operation and 1 means Bist mode. Okay. And since we are adding all these extra hardware components, there will be performance overhead penalties also, because some extra path delays will get inserted due to these Bist hardware that we have inserted. And earlier we had mentioned that if we increase the chip area, the chip yield will also drop. Now, since we are adding some additional components, chip area goes up, so yield will also go down. So, these are the different components of the cost involved in Bist: chip area overhead, pin, we need one additional pin, a little bit of performance overhead, and of course, associated yield loss. Well, of course, in today's multi-million device chips, this yield and chip area overhead are not that important, because the increase will be extremely marginal. Okay. Now, just looking at the overall Bist architecture, let us try to see what are the different, because the primary hardware blocks that we need to activate the Bist and to work just using this. Well, now in this diagram, if you look at, so the circuit that we want to test is residing here at the middle. This is the circuit under test. These are the normal primary inputs and these are the normal primary outputs. So, this is the normal path of circuit operation. So, normally this multiplexer will be selecting this path and this path will get selected. Now, you can see that even in the normal mode, this multiplexer is coming as an additional delay in the path. So, the delay of the total circuit operation will get slowed down a little bit. Now, in the test mode, the test controller will be controlling several things. First is that there will be a hardware pattern generator which will now be starting to generate some patterns that will be applied to the circuit under test. Now, the controller will also be controlling the multiplexer, so that now these patterns and not these PIs will come to the input of the cut COT. Now, since we are trying to evaluate the response also inside the chip, so it is not practical to store all the responses, individual responses and compare, because the number of patterns can be as high as say means 1 million. Okay. So, rather than storing 1 million outputs and comparing them with the good value stored in a ROM, what is normally done is that the circuit responses are compacted. So, after compaction we get a very small value out here. This is sometimes called a signature. So, we do not compare the individual responses, rather we compare only the signature with the corresponding good signature that will be stored in a small ROM. So, after comparison, well, we can announce that the circuit is either good or bad. Okay. So, this is the typical Bist architecture. So, we will have to talk about this pattern generation and this response compaction in some detail. Okay. But before going into these, let us first look at some of the popular general purpose hardware blocks which people use in Bist architecture. Well, you can easily correlate the architecture with respect to this diagram, because we need a pattern generator, we need a response compactor. Okay. Now, there is a general purpose hardware block which has been proposed. This is called built-in logic block observer Bilbo. Now, Bilbo in a sense it is a general purpose logic block. General purpose in the sense that, well, sometimes it can act as a pattern generator, sometimes it can act as response compactor, sometimes it can act as a normal register which is part of the circuit. So, instead of investing in a totally new hardware, what we can do is that some of the existing registers in the circuit, we can enhance them with some additional logic so as to make them programmable in this sense. Now, we shall see later that we can have very simple implementations of this pattern generator and response compactor by slightly modifying the circuit diagram of a shift register. So, all these things can be done very easily, but let us first see the capabilities of this Bilbo, built-in logic block observer. So, as I said, this is a programmable hardware block. Well, with respect to testing, this has the capability to work as a test pattern generator and also as a response compactor. Now, this circuit can work in 4 different modes. One is a normal flip flop mode, it is a parallel in parallel out register. So, in this mode, this register can act as a normal register which is part of the circuit. In the second mode, it can act as a pattern generator, and in the third mode as a response compactor. Now, both these are based on something called linear feedback shift register that we shall come to very shortly. So, this linear feedback shift register is a hardware structure which can be used to generate patterns and also to compact responses. And the fourth mode is that you can configure them as a shift register, so that if you are using scan path, then you can use this shift register as part of the scan chain very easily. Okay. Now, just one thing I would like to mention here before I proceed further is that we are talking about LFSR based pattern generator or on chip pattern generator, but usually what people does is that the kind of patterns that are generated that are not exactly the type of patterns which are generated by a test generator program which we had discussed earlier, but rather what is done, a special hardware circuit is used which can generate very good pseudo random patterns, And I had showed a slide earlier, I had showed a typical graph earlier, that if you feed a circuit with pseudo random patterns and if there are sufficient number of pseudo random patterns, then the fault coverage can also be pretty good. Of course, you can ascertain this, you can verify this through simulation before actually installing and implementing the Bist hardware in place. Before that, you can use fault simulation to find out that, well, actually if I use, say for example 10,000 pseudo random patterns, then what is the fault coverage? If you see or find that the fault coverage is not adequate, we can add some more patterns. Okay. So, in Bist, reducing the number of patterns is not that important, rather the ease or simplicity with which you can generate the patterns, that is more important. Okay. Fine. So, with the capability of this Bilbo, let us take a couple of examples. This is a very simple example. Suppose we have some kind of a circuit where there are registers in between. Suppose this is a register, this is a register, and there is some combinational logic in between. We call it cut 1 and cut 2, and they are connected like this. Now, we have to test this hardware. Now, we can do it very easily. First thing is that we can configure Bilbo into a shift register, and by using that shift register we can use the conventional shift register test which you use for scan path for testing them, that 0011 0011 pattern. So, by that we can test the Bilbo registers. Then what you can do for testing this cut 1, we can configure Bilbo to act as pattern generator. We can configure this Bilbo to act as response compactor. So, now this fellow will be generating the patterns and the output will be compacted here. So, after compaction you can compare with the good value and see that whether it is good or bad. Similarly, when you are trying to test circuit under test 2, then this Bilbo will be generating the patterns and this one will be compressing. Okay. So, in this way, in a normal circuit, by configuring some of the registers as Bilbo registers, we can make this self testing work. Of course, we need a test controller which will be generating the control signals and the necessary sequencing, that the first Bilbo should be generating patterns, this should be compacting. In the second step, the second one should be generating pattern and the first one should be compacting. So, these things should be controlled by a separate small test controller which should also be inside the chip. Okay. Well, now let us take another example which is slightly more complex. Let us take an example like this. These are combinational blocks, cut 1, cut 2 and cut 3. Well, these are some registers, say one here and one here. Now, if you look at the nature of the circuit, this one will be used only for generating patterns, never for compaction. Similarly, this one will be used only for compaction, never for generating patterns, because this is the sink. So, only the middle register, this one should be configured as a proper Bilbo, okay? But the other two should not be as complex as a complete Bilbo register. They can work specifically either as a pattern generator or as a response compactor. Okay. So, here what you can do is that, well, while we are testing say cut 1 and cut 2, this is the testing phase 1, then LFSR 1 can generate the test patterns. These test patterns can be fed concurrently to cut 1 and cut 2. We can test both of these together. Now, the response of cut 1 will be compacted here and the response of cut 2 will be compacted here. Okay. So, testing of cut 1 and cut 2 can go on together. Now, after that, in the testing phase 2, what you can do, Bilbo 2 can be generating the patterns and LFSR 3 can be compacting, so that you can test this cut 3. Now, this process is actually called test scheduling. So, this is a very small example I have taken, but in general this data path will be fairly complicated, and we will have to find out a schedule like this. This schedule for example consists of 2 phases. So, there can be many such phases. So, we will have to find out a schedule which will be taking overall the minimum amount of time for testing. So, you can find out that in some intermediate step we can actually test a number of blocks at the same time. So, we can have some parallelism there. Okay? Fine. Now, talking of the pattern generation. Now, well, we are talking about pattern generation on chip, inside the chip. So, here we have several alternatives. First is that we can have deterministic patterns which are generated by a conventional test pattern generator, and we can store them in a ROM. But the problem is that the size of the ROM will be very large, and this will be an expensive solution. Okay? Because in general these patterns will not have much relationship among themselves, and you cannot use anything less than a ROM to store them. Okay? The second alternative is that many people have proposed this method also, is that you apply all possible input combinations to the circuits under test, which means the test pattern generator will be a simple counter. But the problem is that if the number of inputs is for example 30, then the number of patterns you need to apply is 2 to the power 30. Now, in a practical circuit number of inputs can be as high as 50, 60 or 100. So, then the number of patterns to be applied will become astronomically high, and it is impractical. So, this is too time consuming. Now, the third method, this also many people have proposed. This is something called pseudo exhaustive. Pseudo exhaustive is something like this. Say I have a circuit. Say my circuit has 3 outputs. There are several inputs. Okay? Now, by analyzing this circuit structure, we can find, say for example, this output number 1 is dependent on only these set of inputs. This is called the so called cone of influence, the first 4. The second output, say for example, is dependent on these, and the last output is dependent on the last 3. So, the first output is dependent on these inputs, the second output is dependent on these inputs, and the third output is dependent on these inputs. Now, pseudo exhaustive test pattern, what it says is that you try to generate patterns on the input in such a way that with respect to these blocks, this block of 4, this block of 5 and this block of 3, they all get all possible combinations among themselves. For example, among the first 4 you get all 16 combinations applied. Well, there may be some repetition, but you do not mind repetition, but at least all possibilities may be there. Now, pseudo exhaustive says that the total input here is 8 for example. So, if we apply total exhaustive pattern, it would have been 256, but it says that you try to generate a number of patterns which is much less than 256 and which will cover all possibilities within these small subsets. This is the basic concept behind the pseudo exhaustive. Okay? Fine. And lastly, we have pseudo random patterns. Pseudo random patterns, in fact, this is most widely used because it is the most easily generated one and economical. Well, exhaustive can also be easily generated, but it is time consuming. But pseudo random pattern, we will see that it is easy to generate and it is also quite practical. Okay. So, now let us look at how we can generate pseudo random patterns using a linear feedback shift register. Okay. Fine. This diagram shows you how a linear feedback shift register looks like. See, if you just ignore the circuit on top of this, there are some D flip flops which are connected as a shift register. So, essentially it is a shift register with some additional logic. These circles are exclusive OR gates. Well, you can ignore these for the timing, assume that they are all connected. Okay. So, the outputs of the D flip flops, they are fed to exclusive OR gates. This forms some kind of a feedback network. Some combination of the outputs is XORed and the XOR result is fed back to the input of the first flip flop. Now, the significance of these circles is that it is not necessarily the case that all the outputs should be XORed. So, some of these may be there, say for example, these 3 are there, but this is not there. So, you selectively find out which outputs you want to XOR and you XOR them and feedback at the first flip flop in the input. This is what is called linear feedback shift register. It is a shift register, there is a feedback network, and since exclusive OR is a linear function, we call it a linear feedback shift register. Now, since it is a well defined hardware structure, so once you load it with an initial state, it will always produce repeatable patterns. And it has been proved through extensive experimentation and analysis that the kinds of patterns which are generated by this kind of an LFSR has the desirable randomness properties. So, we can treat them as random patterns, but a true random pattern should not be repeatable. Since this pattern is repeatable, we call it pseudo random. Okay? Fine. Now, with respect to testing, if it is an n bit register, it is not the case that we need to apply all 2 to the power input combinations. Okay? So, the number of patterns that you need to apply is typically much less, say for example 10,000, 20,000, 50,000, that should be sufficient, and the number of flip flops can be as high as 32 or 64. But you need sufficiently long sequences for good fault coverage, but how long, that you should evaluate and find out through simulation. Now, there are other variants of LFSR also. This is one way in which LFSR can be constructed, and another kind of LFSR configuration is there where the XOR, instead of lying outside like this, they are inside this shift register like this. This is called internal XOR based. So, where you have the shift register with the exclusive OR gates in between, and the feedback path from the output you have a path to the input, but some of the XOR gates are also fed from here. Depending on the property you want, you will have to select that which XOR gates you will have to feed. Okay? So, actually these are the 2 different variations. Well, now let us try to look at some of the mathematical properties or mathematical basis on which these LFSRs are based. I told you that you can select these feedback points depending on requirement, but actually how do you select that? But for that, let us first look at some of the mathematical properties of this linear feedback shift register. The first thing we talk about is something called characteristic polynomial. This is something which is associated with an LFSR. So, let us see that what this really means. Well, we start with a sequence of numbers. Let us call them A0, A1, AM and so on. Now, this sequence of numbers with respect to an LFSR, it can be treated, for example, if we have an LFSR like this. So, if this is the output which is fed back, I am not showing the whole diagram. So, this output bit, this will be generating a streams of zeros and ones. So, this output bit pattern, this can be considered as this sequence A0, A1, A2. So, this AIs are 0 or 1. Okay. Now, given a sequence of numbers like this a0 to am, we can define a generating function. So, the generating function can be defined as a polynomial in some parameter variable x. So, this will be a0 plus a1x plus a2x square and so on. So, this you can write in closed form as m equal to 0 to infinity am x to the power m. Okay. Now, suppose we have an n bit LFSR. You have an n bit LFSR. So, let us say these are the corresponding flip flops 1, 2, 3 up to n. Well, now A0, A1 are the bit patterns. So, at the first clock whatever comes out or whatever gets in is A0. So, actually whatever gets out will be fed back here. So, that is what we call A0. So, we are assuming that the initial state of the register is A minus 1, A minus 2, A minus 3, A minus n. And suppose after m clock pulses the current state looks like this: A m minus 1, m minus 2, m minus 3 and m minus n. And in the current state the value that is being fed back at the input out here, this will be am. So, am will be that linear combination of these values, okay, which will be fed back. Fine. So, now if you just look back at that diagram for LFSR again. So, here we had said that the outputs of the LFSR, they are fed back through some blocks H, H1, H2, Hn. Now, this H's can be 0 or 1. If it is a 0, which means that there is no connection. If it is a 1, it means that this is connected. These are simple multipliers. It multiplies with either 0 or 1. Okay. So, either this is present or not present. So, what I can say is that this a minus 1 to a minus n, these are the states at the present instant, and based on the linear combination of that we are generating this am. So, we can write down this am as follows: I equal to 1 to n h I a m minus I. So, if I is 1, h1 a m minus 1, just to observe, h1 is the weight associated with the m minus 1, h2 m minus 2 and so on. Well, with this am, now again you go back to the expression for gx which we had computed earlier. So, gx we had said is m equal to 0 to infinity a m x to the power m. Now, this we can write like this. Instead of am we can substitute this, I equal to 1 to n h I a m minus I x to the power m. So, instead of am we have written down this expression. Well, now we can reorganize this a little bit and we can write I equal to 1 to n, we can take out this h I and x I. We can out of x to the power m, I take out x I here. So, what remains is m equal to 0 to infinity a m minus I x m minus I. This is what remains. So, this I can reorganize and write like this, because x I and this product is x to the power m. Fine. Now, this again the first term remains the second term, if we expand this, the first few terms are this, and finally you get m equal to 0 to infinity am x to the power m. Now, this is nothing but gx, this is nothing but gx, and this term, this a minus 1 to a minus I, this is nothing but the initial state of the LFSR, okay, the initial value which was loaded. Fine. So, by reorganizing the equation, taking gx on this side, we can, and if we just solve it a little bit, you can get the final expression for gx from here. Gx becomes equal to I equal to 1 to n hi xi this part a minus 1 x to the minus 1 divided by 1 plus I equal to 1 to n hi xi. So, this is the final expression for the generating function. So, if you look at the numerator is something, there is a part which is the initial state of the LFSR, and of course, we have a term this hi xi, but the denominator is something which is a polynomial of degree n. So, the denominator, if you expand, and the denominator is typically denoted by px. Okay. So, if you write down the expression for px now from here, so px will become 1 plus h1x plus h2x square plus hn x to the power n. Now, this polynomial px is defined or is called as the characteristic polynomial of the LFSR. Now, it is this characteristic polynomial which defines some properties of LFSR. See, if we look at the patterns which are generated, you look at the patterns which are generated by an LFSR. Just one thing you can immediately observe, that if you consider the all zero pattern, well, if you load the LFSR with the all zero pattern, then you can see that the LFSR will always remain in the 0 state, it will never come out of it, because you are feeding back through an XOR function, and an XOR function with a set of zeros fed to the input will give a 0 as the output. So, it is 0 which will again be fed back. So, an all 0 state will leave the LFSR indefinitely in the all 0 state. So, once you have all 0 pattern in the LFSR, so LFSR will remain in that state. Okay. So, this all 0 pattern you cannot load. Now, there is another kind, you can say, the characteristic polynomial that we have defined. Some of these characteristic polynomials are defined as primitive. There is a concept of primitive polynomial. The idea is that the characteristic polynomial px is called primitive if the periodicity of the LFSR is 2 to the power n minus 1. Well, what do you mean by this? Now, we have an n bit LFSR. So, an n bit register potentially can be in 2 to the power n possible states. Now, out of the 2 to the power n possible states, we have just said that all 0 state is ruled out. Once it gets into all 0, it will remain there. But a primitive polynomial is one in which if you start the LFSR with any non-zero state, it will go through all 2 to the power n minus 1 other patterns and then it will come back. But unlike a counter, it will not go through the state sequentially 1, 2, 3, 4, 5. Rather, it will go through in a pseudo random order. This is the property of the LFSR. The successive patterns will bear some randomness properties. There will be no two patterns which will be repeated, but yet you can cover all 2 to the power n minus 1 patterns. This is the very interesting property of a primitive polynomial which you can use in the LFSR. So, Px is primitive if the periodicity of the LFSR is 2 to the power 1. So, these kind of primitive polynomial is very useful in Bist application. Very useful because suppose you start with a 32 bit LFSR, but depending on actually how many patterns you need, you can potentially go up to 2 to the power 32 minus 1, so many patterns. So, you have entire flexibility. But if you take an LFSR whose characteristic polynomial is not primitive, then possibly you will see that well you can generate only 2 to the power, say for example 10 patterns. So, after every 1024 patterns, the patterns get repeated. So, you really do not want that. You will want a LFSR as a pattern generator which can generate pretty large number of patterns as you need. Okay. So, LFSRs that realize the primitive polynomial is very desirable in that sense. Okay. Now, if we look at the standard textbooks for this kind of linear machines LFSR, you will find that the primitive polynomials of various orders are listed. There are methods to find out whether a polynomial is primitive or not, and through exhaustive, you can say, simulation and experimental studies, people have find out a list of all primitive polynomials up to very large values of n also. So, I am showing you some, I am giving you a few examples, these examples of primitive polynomials. Suppose n equal to 16, you have a 16 stage LFSR. Now, in the book you will find it says that the primitive polynomial is 5, 3, 2, 0. This actually means that the polynomial, characteristic polynomial is 2 to the power 0, 1, 2 to the power 2 x square, not to the x to the power 0, x to the power 2, x to the power 3, x cube, x5, of course the last one will be there, x16 is implied. You take n equal to 24 say, for 24 you will see that a polynomial like this is listed 4310, which means Px is 1 plus x, x cube, x4, x24, say n equal to 32. 28, 27, 1 and 0. For this Px is 1 plus x to the power 27, 28 plus 32. So, the idea is that you select the number of bits of the register first, how many bits you need, then you select a primitive polynomial. Once you have the polynomial, you construct an LFSR with so many flip flops and you take the feedback point from these. These are the, you can say, flip flop numbers from where you need to take the feedback and compute the XOR and feedback. So, it is a fairly simple process. So, if you construct an LFSR like this, you will get a structure which can generate very good pseudo random patterns as per your requirements. Okay. Now, I had mentioned earlier that well, this LFSR acts as a good pseudo random pattern generator. Now, pseudo random pattern generator, a pure pseudo random pattern generator has a property that in each bit position the probability of 0 and 1 are exactly the same. So, probability or the signal probability set is 0.5. Signal probability is the probability that the line will be having a value of 1. Now, since the patterns are random, the probabilities of 0 and 1 are equal. Now, in many circuits it has been found, and there are many works which have been reported in this regard. There people say that, well, instead of pure pseudo random patterns, if I apply weighted pseudo random patterns, that my fault coverage may improve. So, weighted pseudo random pattern means, well, you consider an AND gate. You take a 4 input AND gate. Now, in order to test a 4 input AND gate, say for example, I want to test the output stuck at 0 fault. So, for testing the output stuck at 0 fault, I have to apply 1 in all the 4 inputs. Now, if the signal probability of each line is 0.5, I am saying that you have an AND gate, the signal probability of each line is 0.5. So, the probability that the output will be 1 will be 0.5 to the power 4. This is a very small number, okay, which means that if you apply pure pseudo random patterns, the probability that you will get a pattern which will generate a 1 in the output is very less. So, for this purpose, possibly you will have to generate a weighted random pattern whose input probabilities are higher than 0.5, right. Okay. This can be done very easily. So, I have a suggested scheme out here, where in the first place you ignore these AND gates, we have an LFSR, we have a 8 stage LFSR. Now, this 8 stage LFSR, you know that it generates pseudo random patterns. So, you take the output from any bit position, the signal probability will be 0.5. Now, the interesting thing is that suppose I have an AND gate and I feed the AND gate with 2 inputs whose signal probabilities are 0.5 and 0.5. So, what will be the signal probability of the output? The output will be 1 if both the inputs are 1. So, the probability will get multiplied. So, the output probability will be 0.25. So, you see that the individual line, say you take the output of this, here the signal probability is half. You take an AND gate, you take any 2 outputs and it 0.5, 0.5, so output becomes 0.25. And you take another AND gate where one of the inputs you feed with a probability 0.25, the other you feed with 0.5, then what will be the output then? 0.5 into 0.25, this will be the signal probability. So, it will be 0.125, this is 1 by 8. Similarly, 1 by 8 and 0.5, you put another AND gate, you have 1 by 16. So, in this way you can have signal probabilities 1 by 16, 1 by 32, 1 by 64 as you wish. Okay. So, this can be a multiplexer, depending on this weights you can select the multiplexer. Now, in addition, whatever you get, for example, you get just for the sake of discussion, let us say you get a probability of 1/4 here by selecting this line. Now, you have an XOR gate in addition. Now, if we apply this inversion input as 0, so the same signal will be coming out. So, you will be get 1/4 probability in the output. But if you apply a 1 in the inversion, then this XOR gate will be acting as an inverter. So, the output signal probability will now become 1 minus 1/4, which is 3/4. So, by this simple structure you can get so many different values of the probability. So, this table lists all the possibilities. So, you can have this half, 1/4. By setting the inversion to 1 you can have 3/4. Similarly, you can have 1/8. By setting inversion to 1 you can have 7/8. Similarly, 1/16 and 15/16. So, in this way, well, I have taken a very simple example with 3 AND gates and 1 XOR gate. You can increase the number of gates, you can use other kinds of gates. So, you can generate a circuit which can give you a number of different values of signal probabilities or weights. Now, using that you can use, you can compose a pseudo random pattern generator where the signal probabilities can be any arbitrary value, well, up to certain resolution. It depends on how many gates you are using. More the number of gates, higher resolution you will get. Okay. So, this weighted pattern generator in Bist, this has been well explored, and in fact many people also suggested use of this, but in practice its use is not that popular. Well, so we talked about how to generate the test patterns in a Bist. We had mentioned that this LFSR is a structure which is very extensively used, and LFSR has some very interesting properties. It can generate pseudo random patterns. If you choose a primitive polynomial, then you can have 2 to the power n minus 1 so many patterns if you need them. So, you can excite the circuit inside the chip with the pseudo random patterns. So, now the next question is that what do we do with the circuit outputs that we get? As I said, we cannot individually compare each circuit output as it comes. So, first we will have to reduce them through some kind of a compaction, then only we can compare. Now, in our next class we shall see that how we can carry out this compaction again using a very similar structure using linear feedback shift register. This we shall be discussing in our next class. Thank you.